Hey everyone, welcome to homework 3.18. Sorry this is so late. Unfortunately got caught up in a lot of things today. So today we looking at growth rate versus growth factor. Remember, the growth rate is how much it is increasing or decreasing, but the growth factor is that either 1 plus the growth rate or 1 minus the growth rate. So if we have a 30% increase, it is increasing, which means our total number needs to be greater than 1. So in this case, we would make this a decimal, which is 0.3, and then we're going to add 1 to that. So it would be 1 plus 0.3 or 1.3. That is your growth factor. 30% decrease now, we're doing 1 minus 0.3 because we're looking at what remains, which is 70% or 0.7. Here, a 2% increase. Again, with 2%, be careful, you're going to move that over 2 decimal points. So this would be 1.02. 2% decrease. Now here we're doing 1 minus 0.02. So this would be 0.98, right? 98% is left after a 2% decrease. So this would be your factor. 0.04% increase. Now this is tricky because there's already a decimal in there, but don't worry. All you need to do is move that decimal over 2 points or divide by 100, right? And so now we're going to have a 1.0004 as your factor. Here we're doing 1 minus 0.0004 and getting your factor there. So you can calculate that. Go ahead and put that there, but this is subtracted from here because it is decreased, and so we would have point, right? What percent left of our whatever amount it is, right? Of our original amount. Okay, if we have a 100% increase, now we have 1 plus this in a decimal form is just 1. So if we have a 100% increase, we're doubling something. So then your factor is 2. All right, so you can reason through that. 100% increase means I'm doubling. If I have 6 and I have 100% increase, I now have an additional 6, or times 2, right? So it is doubled to 12. In 1990, the population P of India was about 870.5 million people. By 1995, there were about 960.9 million people. Right, so that's the increase. The equation approximates the number of people in millions in terms of the number of years since 1990. By what factor does the number of people grow in 1 year? So here we're looking at the factor, so that is 1.021. If we're looking at the rate, then we're looking at 2.1%, which we see here, right? Moving that decimal point over, 2.1%. If D is time in decades, write an equation expressing the number of people in millions, P in terms of decades. So P equals 870.5 times 1.021 to the power of 10 to the power of the decades. Now you can also calculate this piece right here for the decade to see what that would be, because this would give us the factor for a decade. So if you'd like to calculate that, you can, or you can write it as this, because if we then input that decade into your calculator, you'll be able to find an answer. Use the model P equals 870.5 times 1.021 to the power of T to predict the number of people in 2015. So we're comparing 2015 with 1990, which gives us 25 years. So we have P equals 870.5 times 1.021 to the power of, 25. All right, yes, 1990 to 2015, right? And so then I do want you to go ahead and actually calculate that. So again, go ahead and use the calculator and actually calculate and fill that in. The 2015, the population of India, that's awkwardly worded, population of India was 1,311 million. How does this compare with the predicted number? So you want to compare this with what you got up here. Is that accurate or not? So a yes or no, or it is close to it, or it's a little bit different, which would make sense, right? Because we're in real world versus what we're looking at is a exponential function. An investor paid $156,000 for a condominium in Texas in 2008. The value of the homes in the neighborhood have been appreciating, so this is increasing. We should be looking at 1 point something, 12% annually. Select all the expressions that can be used to calculate the home in dollars after T years. All right, so if it's appreciating by 12% annually, we're looking at a 12% increase. So our factor would be 1.12, right? So this one is not correct because we are missing that 1 in front of it. We can see B is correct. C is the same thing. 1 plus 0.12 is 1.12. Now here we're subtracting. That would be if it said depreciating, but it says it's appreciating. So that is not true there. And then this one says if we are dividing it by 12 months. So this one would, in this case, not be true because it didn't say 12% each month, compounded monthly, right? It says that it is, or compounded monthly with a nominal interest rate. And so this one in this case is not representing this particular situation. If it said 12% annually is the nominal interest rate and it is compounded monthly, then we might be looking at this, but this years piece would still not be accurate, okay? Because this is by month and then this is by year. Number 7, a credit card has a nominal, so here we have that nominal interest rate of 18%. That's what they say it is for the year, but it is compounded monthly. So here's that part where we need to divide. The cardholder uses the card to make a $30 purchase. Which expression represents the balance on the card after 5 years in dollars, assuming no further charges or payments are made? All right. Now, in this case, we're looking at compounding monthly 18% interest. So that 0.18 needs to be divided by 12. That amount that I'm going to owe is going to increase, right? And so it's going to be 1 plus, and then we have our starting amount here. So now you need to think about that decimal, or sorry, that exponent rather, not the decimal, the exponent. So this is in months, right? So if this is in months, we also need to have our exponent represent the number of times that it will be compounded over those 5 years. And if it's happening monthly, it will happen 12 times, and then per year then it's going to be times 5. So D is our best answer, because this represents if I'm compounding monthly for 5 years, I would be compounding it 60 times, right? And so that 12 times 5 is that 60, and this 0.18 divided by 12 is taking this 18% interest and breaking it up monthly, and so that would get us the most accurate results. For A, I'm just going to go through this so you know. A, they did not turn that percent into a decimal. B, they added it to 1, which is good, but they forgot about the division of 12 piece, right? That this needs to be broken up because this is the nominal interest rate. All right, number 8, the expression represents an account balance in dollars after 3 years with an initial deposit of $1,500. The account pays 8.5 interest, which we see right here, compounded annually for 3 years. Compounded annually means 1 time per year. Explain how the expression would change if the bank had compounded the interest quarterly for 3 years. So if they were compounding the interest quarterly for 3 years, then we would need to break up that 8.5% interest. So let's write out what that would look like. So we would have our initial amount of 1,500 times 1 back. Here we're going to do 1 plus 0.085 divided by, if it's compounded quarterly, it's compounded 4 times, so divided by 4. And then if it's happening 4 times, it's to the power of 4, but also we're talking about 3 years. So describing this or explaining it is we would have to split the interest or divide the interest into 4, right, percents that we're doing, dividing that by 4, and compound 12 times, because we would compound 4 times in 1 year for 3 years, and so this would be compounded 12 times. Write a new expression to represent the account balance in dollars if interest is compounded quarterly. So actually that's already what Ms. Lee did. If you want to, you can go ahead and rewrite this as 1,500 times 1 plus 0.085 divided by 4 to the 12th power. You can also write this by calculating that out and putting the actual decimal there. So if you would like to, I would suggest you go ahead and compare those two, because those two are equivalent expressions. Number 9, the function f is defined by this function here. It represents the amount of money in a bank t years after it was opened. How much money was in the account when it was opened? That's $1,000. Sketch a graph. Here you can go ahead and take a look at your calculator. It is increasing, so your graph should definitely be increasing, right? And you're starting at about 1,000 and going up. So I would go ahead and estimate that. You can go ahead and also graph that in your calculator and sketch a little graph there. Doesn't need to be perfect, but you should be able to show me that that's an upwards curve. It's increasing, and it's increasing by very little, right? 7%. So it shouldn't be a super steep curve either. When does the account value reach $2,000? So here, I would encourage you to put this equation in your calculator, and then you can look at the table. So let me show you how to do that. All right, so in my calculator, I've gone to y equals and put 1,000 times 1.07 to the power of x, which is our function. I'm now going to go second table, and we're going to look at the table, and we want to see where does it get above 2,000. And so it happens, it looks like between 10 and 11. So let's go ahead and go back here. When does the account value reach 2,000? Now this was t years, so this is between 10 and 11 years. That table function is really, really important then. You could also go ahead and test values for t and see when you get to that point. That would also work. Number 10, the graph shows the number of patients with an infectious disease. Ooh, it's increasing over a period of 15 weeks. Give an example of a domain for which the average rate of change is a good measure of how the function changes. So at what point is the average rate of change, the slope, a good measurement? Really, we're only looking at this very beginning part, right? Remember, those small sections are where we're going to look at average rate of change being good. So I would say maybe 0 to 3 weeks might be a good example. But after that, it's starting to get increase at a much faster rate. And so then it is no longer looking at a really great rate of change. You might also see like it's pretty even here from 4 to 6. That might be okay as well, because we're looking at, again, a very small amount of time and therefore a small increment of increases. So you could also say or 4 to 6. That would also be okay. Give an example of a domain for which the average rate, remember domain is your x values, for which the average rate of change is not a good measure of how the function changes. Okay, well really, like if you were to do 0 to 15. 0 to 15 is terrible, right? Because if I were to calculate the slope of this line, it's going to be pretty steep compared to here, but then not steep enough compared to this line here, right? So here, this average rate of change would be much too big, but here the average rate of change would be much too small. All right, number 11, a party will have pentagonal tables placed together. The number of people P who can sit at the tables is a function of the number of tables N. So this is the function. It says explain why. So A is because we have those 3 times the number of tables plus 2. So let's see where we see this here, right? So we have the number of tables here is 2. So that would be 3 times 2 plus 2, 6 plus 2. And this is because we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 people can sit there because here we lose 2 sides of our pentagon, right? We lose this side of the pentagon and we lose this side of the other pentagon. And so what then is left is 8 seats. So you can use this example, or you can also say, The 3 plus 2 gives us the number of seats that are then available once they are connected. If we look down here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 seats. And so here we would have 3 times 3 tables plus 2. So you can have 3 seats at each table times the number of tables plus those 2 additional seats. How many tables are needed if 47 people come to the party? So if our equation is 3n plus 2 equals p, the number of people that can sit, we have 47. So then you can solve for n. All right, so letter B, go ahead and solve for n and see what you get. Remember that if you get a number with a decimal, you're going to need more tables, right? So just keep that in mind. That right here, though, I'm going to highlight because that's an answer you need to calculate. You know how to solve this equation for n. What about 99? So 3n plus 2 equals 99. Same thing, solve for n, see what you get. If you get a decimal, you're going to need another table. D, write the inverse of this function, explain what the function tells us. So this is a review of those inverse functions. I'm going to write p equals 3n plus 2. The inverse is if we solve for n, so minus 2 on both sides. And then we would have p minus 2 equals 3n. Now I need to get n all by itself, and so I'm going to need to divide by 3. So n equals p minus 2 divided by 3. It's a nice literal equation, inverse function there. All right. Okay, that is it for your homework. If you have any questions, please let me know. Today's code word is post-it. Again, it's post-it is your code word. Go ahead and write that at the top. Ms. Goodall will collect your work from this particular assignment. And then tomorrow, remember that she will be with you for your classwork. All right. If you have any questions, feel free to reach out. Happy homeworking and see you next week.